Hi folks, my name's Dr. Graham Bird. I'm a reader of physical geography within the School of Natural Sciences at Bangor University. Thank you very much for joining us today on this virtual visit day. I hope you sort of get all the information that you need to help you with your decision making. What I'm going to do for a short while is just to give you a little bit of an introductory talk to a topic which I spend a bit of my time working on, and one which sort of links to a number of themes which are covered within our geography and also within our environmental science degrees here at Bangor, and that's on the issue of metal pollution. So what I'm going to hopefully do is sort of exemplify to you why I think it's actually one of the most important current but also future global environmental problems. Okay, so a little bit of context for you. Now, for thousands and thousands of years, we've used metals as a society for lots of different purposes. From simple tools right the way through to the complex electronics in your smartphone. We need to use metal resources to underpin society, if you like. Now, importantly as well, we humans, plants and animals as well, also need an amount of certain metals in their diet for good health. For example, we need relatively small amounts of, for example, copper or zinc and iron, for example, for good health. Too little of that can cause problems, but then equally too much can also cause problems as well. However, importantly, there are also some metallic elements which have no known biological functions, so things like lead or mercury, for example, or cadmium, which can be toxic to humans, toxic to plants, toxic to animals at relatively low concentrations. So there is concern when our use of metals potentially means that their concentrations within the environment are relatively high. Okay. Now, obviously, we access metal resources by digging them out of the ground, and that process has generated, as it says there, colossal amounts of both solid and liquid wastes, which creates an environmental risk. We have to deal with that waste product, and as it says at the bottom there, now that has a cost to it as well. So actually, and this is a couple of years old now, that number, that estimate, but simply for dealing with drainage water, polluted or potentially polluted drainage water from metal mining activities, we estimate the cost of that would be something like $100 billion. So it's a real, big cost in terms of trying to deal with cleaning up potentially around some of these potential pollution sources. Now, I quite like this, is a bit of a visual sort of bit of a prompt to the scale of the problem in a way, and the scale of the problem of dealing with sort of mine waste. So what we've got here is an open cast metal mine in Kalgoorlie in Western Australia. And you can see that the open cast pit is about 2.4 kilometres long. We can work that out from Google Earth quite handily. But then just up to the sort of the right-hand side here, we can see the waste pond. It's called a tailings management facility, or a tailings pond. I'll tell you what tailings is in a second. Basically, it's sort of particulate waste left over from the mining process. The footprint of the waste pond is longer than the footprint of the actual mine itself. So it gives you an idea of the scale of the problem and the amount of waste that we generate, which we've actually got to deal with safely and ensure that it's not posing a potential environmental risk. Now, one of the risks that comes from mining activities is that drainage water that stems from it can be potentially acidic, And there are a range of of chemical processes which generate that acidity, and also, importantly, different bacteria can play an important part of that. Now, not all mine drainage is acidic. It requires the right kind of characteristics, particularly the presence of iron sulfide minerals in the material that's being mined, and it's the oxidation, ultimately the oxidation of those iron sulfides, plus some other processes, which generates that acidity. So not only is acidic water potentially damaging to the environment, but that drainage water, particularly from metal mines, can also be sort of metalliferous or metal rich, and potentially therefore releasing high concentrations of metals into the environment, with the potential risk there for environmental health, or maybe potentially also human health. And in a way, though, you can sort of think of mine drainage sort of at one end of the spectrum, if you like. It's sort of the relatively little but constant type of process that creates that risk. And importantly, we can get some really weird and wacky and pretty amazing chemistries in this sort of mine drainage. I'll just draw your attention to this this table here. A lot of you will hopefully just be aware of the pH scale, a measure of acidity versus alkalinity. And we often commonly think of the pH scale as running from 1 to 14, with sort of 7 being neutral. Now, don't think that, because we can have negative pHs. So we've got here some data from some acid mine drainage, and some very acid mine drainage from a mine in California. What we can see here is pH is down at minus 3.6 pH. Now, so pH is a measure of the hydrogen ion concentration in the water, the inverse log of that concentration. So we can have negative pHs because the hydrogen ion concentrations are so high. But, this is fairly extreme, but extreme is always good. It's always interesting. So don't anybody ever don't let anybody tell you that pH has got to be between 1 and 14, because we can see here it can easily be much less than that. So the acid mine drainage chemistry can be pretty spectacular, not only perhaps in terms of pH, but also maybe in terms of the metal levels that sort of go with it. And it's something we actually see quite close to Bangor. It's one of the processes that we sort of demonstrate and teach to our undergraduates. So we're sort of Bangor's here on the lower of the red circles, just on the coast there, just on the Menai Straits. And we've got sort of Snowdonia just to the south and sort of the southeast, and the upper circle, the upper red circle on Anglesey is circling a place called Paris Mountain, which from above looks like this. It used to be the world's biggest copper mine back in the sort of the 1800s or so, and from the ground looks pretty spectacular. Looks like this, and this is a great site that we take our students to teach them about some environmental issues and environmental pollution processes. In particular, it's also a site of special scientific interest for some pretty wonderful geology as well. And it's also a great site that demonstrates particularly processes of acid mine generation on this site. And it's a site that's been actively polluting local river systems in particular for decades. It's also a good site to discuss some of the issues and strategies that have been taken to try and reduce the risk posed by this now abandoned former copper mine. At the other end of the extreme, as I say, acid mine drainage is sort of perhaps a little bit, but over long periods of time. We have what are called mine tailings dam failures. These are like sort of very spectacular, potentially high in magnitude but low frequency events. And this is where we have spillages of mine tailings and associated water that's been stored within ponds. And that mine tailings is the fine-grained waste left over from when we separate out the metal from the waste rock, and we store that tailings in ponds or sort of tailings dams or tailings management facilities. And they look a bit like this, you know, they're sort of different designs, you know, from, for example, a dam built across a river valley, the tailings pumped in behind, or a structure built on flatter ground. You know, we pump that potentially metal-rich tailings into the ponds as where it's stored. Okay, the one on the right is down for a former tin mine in Cornwall called Wheel Jane. And some of them, you can pick them out on Google Earth if you sort of get your eye in, so to speak. This is a pond in Bulgaria, and you can see the dam has been built across at the lower end of this valley, and that the whiter tailings has been pumped in behind it, stemming from the open cast mine that's up to the top. So they're pretty big, some of these features, pretty spectacular. The problem we have is on occasion we have failures. The dams holding that material fail for a range of different reasons, and you know, sometimes they go somewhat unreported. Other times they're big enough that they make the news. There's been a couple recently in Brazil, for example, which will unfortunately cause sort of loss of life. And there's one fairly recently, a couple of years ago in 2014, that I've been doing some work on in British Columbia and Mount Polly, which was one of the biggest on record at the time, and sort of still is. And we can see the dam breach there, and that material that sort of spilled out of the dam sort of plugged up here and then flowed off down to the right, down what's called Hazeltine Creek. And we can see some before and after images here, and we can see the retention basin, the dam before, and then below, and you can see Hazeltine Creek. You can see all that yellowy coloured spilled material, which is now stored and been released and deposited within that river system. And actually what it does, it links to another issue that goes sort of hand in hand with the pollution side, is that these events can often cause major geomorphic disruption to river systems. You know, we're releasing large flood waves of water and or releasing large amounts of particulate waste into recipient river systems. Well, that causes a major sort of geomorphic disruption. And actually understanding the principles of geomorphic process and geomorphic control within river systems, how river systems work, if you like, is one of the themes that we teach across our, particularly our geography degrees, for example, in our sort of catchment processes module. And what we've been able to actually identify with this event is that we've been able to look at the pollution legacy, so how polluted was the released material, the spilled material, and sort of where is it now. But actually, we've been able to work out that what that flood wave did as it was released is it initiated a large amount of erosion within the river catchment. It was eroding the existing floodplain material, etc., as it went, which we sort of might expect. And that not only creates major geomorphic disruption. So this image on the left here, you've got a pretty big American pickup truck for scale. Well, all that erosion was caused by the flood wave from the tailings spill. So we get pretty big scale geomorphic disruption. But that erosion also then, I guess a slight sort of benefit though, is what that erosion did is it dilutes down the metal concentrations within the tailings that have been spilled, and then it means that the material that's been deposited on the floodplains and in the riparian zone, and has been also released into the lake at the end of the system, actually then is a mix of tailings and eroded catchment materials. And actually, as you get further down the system, a greater proportion of that is eroded catchment material. And actually that erosion and that mixing helps to dilute down the metal concentrations within that material, and sort of does help a little bit to ameliorate against the environmental risk. But then obviously what you've got is major geomorphic disruption in that system, which has then got to sort of re-establish an equilibrium over time. So it's actually been quite a little bit of a new way of thinking, actually, slightly around the potential magnitude of those erosive processes that occur We often tend to focus as much on the pollution, and maybe we also do need to think a little bit hand in hand with the geomorphology. As I say, but these things are pretty spectacular, and you get some fairly hefty sized boulders being quite easily carried over several kilometres distance by events of this scale. As I say, so we have been sort of looking at the pollution aspect and some of the skills that and the techniques that I've been using in the field to measure metal concentrations in soils and sediments and waters. They're equally ones that we teach to our students, and some of our students also undertake sort of their final year projects, looking at sort of issues around metal pollution in waters or sediments or soils and things like this, and looking at maybe spatial trends or temporal trends and stuff like this. So we're actually able to teach a lot of the very practical field skills, which a number of our graduates have since gone on to use in sort of postgraduate employment and go and work in sort of work for consultancy companies, for example, or for example maybe with the Environment Agency or others, where actually they're doing work like this, looking at pollution type problems, maybe in slightly different contexts, but using these inherent basic skills. And the last thing I want to say is, sort of looking forward, is maybe the risks could continue around the issue, particularly of the risk posed by these tailings dam failures. As we know, our climate is going to change, predicted to get an increase in extreme weather events in particular, and particularly storminess in certain parts of the world. And that's what that bottom figure here is showing, changes to the predicted wettest month. And often it's storm events and excess rainfall which can be a trigger for these tailings dam failures in particular, because you get excess water within the ponds. So actually a bit of work ongoing in a minute is to try and look at where in the world we've got most tailings ponds and most mining history, most potential pollution problems, and how the climate in those places will change and what that might mean, not only actually for tailings dam failures, but for a variety of processes that help to create pollution problems. So, for example, how might acid mine drainage generation evolve if we have either maybe a wetter climate or a drier climate, or a climate that's, say, got potentially increased storminess. So that link to climate change and the big overarching environmental issue of our time, and I say one that we cover from various different aspects through our degrees at Bangor. We can see here played out very clearly linked to sort of environmental pollution problems. Okay, so hopefully that was a bit of a whistle-stop tour. Hopefully you've learned a few new things, picked up a couple of ideas, just been introduced with just a few of the things that we do here in Bangor. So thank you very much for listening. Hopefully, as I say, you're sort of enjoying sort of getting to know a bit about us. There's a couple of links on the screen there for how you can sort of get more information about the university and the school and geography, and a couple of ways you can follow us on social media as well. So I should say thank you very much for your time. Do please keep in touch with us. Do please make sure to get in touch if you've got any questions, and I shall hopefully see you all very soon. All the best now. Bye-bye.